Hello, I'm Pradeep. Today I'm going to talk about a project which is Hedge optimizing long-term cloud costs by mixing VM purchasing options, which is in collaboration with Noman and advised by Professor David Irwin and Prashant Shanna. First, let's talk about cloud platforms and their increasing complexity. In the recent time, cloud platforms have grown rapidly thanks to their popularity and increased usage in industry and enterprise environment. As a result, cloud platforms have tremendously become complex as they must manage physical and virtual resources and huge data centers taking power and cooling into account. Also, they need to account for growing and shrinking resources allocated to users on the fly, as scalability is a key unique selling point of cloud platforms. And also, they have to offer various computing services like VMs, database, etc., in order to support end user applications. Just coming to virtual machines, cloud platforms offer several dozen of them with different CPU, memory, network, disk configuration, etc. And note that each of this unique offering costs different price as well. Also note that each of this VM type, cloud platforms offer them under different purchasing terms and options where they differ across multiple dimensions like time commitment, price, priority, availability guarantees, etc. Popular cloud platforms like Amazon, AWS, EC2, Google GCP, Azure offer some common purchasing options like on-demand VM type, reserved VM type, transient VM type, which we'll go in detail now. First, let's talk about on-demand VM type. This is the most popular VM type and is usually the default option in most of the cloud platforms where users can rent these resources type at any time and can terminate them until they need. They are typically billed per unit time, where in the recent times, most of the cloud platforms have moved to per second billing and they require no time commitment from user at all. On the other hand, reserve VM types require long commitment. You're looking at either 1 year option or 3 year option. And in exchange for long duration time commitment, cloud platforms offer them at a steep discount compared to on demand. And note that users are billed for entirety of this duration, irrespective whether they use these resources or not. Another key difference is that reserve VM types have a higher priority when it comes to allocating the user resources. Apart from these two cloud popular options, cloud platforms offer their idle capacity as transient VM types, where they are similar to on-demand VM types, but there are few differences like they are offered at steep discount like 20 to 90% compared to on-demand. But in exchange for cheaper price, cloud platforms reserve the right to revoke them at any time if a higher priority request comes in for resources. Also note that they come with no time commitment. But they are slightly riskier than on-demand, hence they are mostly used for non-interactive workloads. Here the graph shows how these three different cloud purchasing options stack up in terms of multiple dimensions. Here we show cost per hour, and on x-axis we have two things. One is guaranteed, non-guarantees. These resemble priority, and then revocability and non-revocability corresponds to revocation frequency. As you can see here, spot VMs or transient VMs are cheapest, but they are lower priority, as well as they can be revoked at any time by cloud platforms and vice versa. And other platforms are slightly expensive as they are non-revocable and priority changes as well. Apart from these common options, there are some unique offerings from cloud providers as well. For example, Google Cloud Platform offers sustained use discount, which applies automatically to all on-demand VMs based on their monthly usage, where it rewards users for using same VM type continuously. Also, they offer customized VMs where they allow users to create their own VM types by selecting how many CPU cores they need, memory they need, etc., as opposed to picking standard VM options. On the other hand, Amazon EC2 offers spot blocks, which are slight variation of spot or transient VMs, where users can rent VMs in terms of per hour basis and also build per hour, but they have less revocation frequency, and also you can select of maximum of 6-hour blocks. Coming to scheduled reserve, these are slight different take on reserve VMs where users can reserve VMs for repeatable daily, weekly, or monthly schedules. And note that users have to at least select schedules that amasses total of at least 1200 hours across the year. Given all of this information on cloud complexity and cloud offerings, the challenge for organizations or private clusters in order to migrate their workloads to cloud platforms is how to optimize long-term costs, as this requires taking into account uh, what type of VMs I need to buy, also under which purchasing options. The first problem statement here is that selecting right set of VMs. This requires knowledge of workload characteristics like resource usage, etc. And it has been subject of much research in the past. Example, cherry pick NSDA 2017. The later problem statement, which involves selecting right mix of purchasing options, requires future workload expectations, and this requires balancing two key trade-offs, where do you want highest cost savings where users can pick long-term reserve VMs, or you want to retain the flexibility to respond to changing workloads by selecting more on-demand VMs. Hence, in order to address this problem statement, we design policies to optimize long-term cloud costs by selecting a mix of VM purchasing options based on both short-term as well as long-term expectation of workload utilization. Now that we have seen motivation, introduction, background of our work, let's go into our design section. First, let's talk about our long-term optimization policy high-level goals, which is to select VM and their purchasing option to minimize long-term cost to execute the workload, taking into their characteristics. Here, we assume a bunch of things. First thing is the workload should consist of batch submissions from users, where each batch submission can consist of several different tasks, where each task comes with what are the requested cores and memory size to run that task. In order to do that, we designed two key policies. One is optimal offline policy and another is practical online policy. First, let's talk about our offline policy. Our offline policy is an ideal policy that results in minimal value and can be treated as opt value, where we cannot minimize the cost beyond this policy output. In order to compute this opt value, we make some unrealistic assumption to start with. First one, we assume precise knowledge of future workloads, where we assume when the job's gonna come precisely, as well as what are its requirements and how much time does it take to run it. And second, we assume a fractional supply and demand. That is, we assume that we can buy the compute resources in terms of unit resources, where it can be CPU or memory, and at the same time we can assume that each job can be subdivided into smaller jobs so that we can fit onto this unit VMs as well. Hence, as a result, it is not realistic and can be only used as a benchmark to compare more realistic policies. First, let's talk about how the basic approach or intuition behind optimal offline policy is. First, what we do is we transform our workload as a time varying function of resource demand, where we take the workload trace and we aggregate resource demand per unit time. For example, this curve shows aggregated core demand across the time period over the year. As you can see, that core demand varies across the year drastically. Next, what we do is, given this time varying function of resource demand, we, for each time unit and for each of the time resource demand for that time unit, we try to pick cheapest option by first computing normalized cost for that resource demand under each purchasing option. Next, we select the purchasing option that results in cheapest normalized price. Note that normalized price for each purchasing option differs widely and it has to be computed differently as well. Afterwards, we repeat this process until all the resource demand across all the time slots is satisfied. Note that computing normalized cost is a key contribution in our work and is non-trivial, as we need to consider several things like time commitment of purchasing options, whether the VM option is revocable, and we have to take job length in the case of transient VMs as well, and price, etc. First, let's start with simplest option here, that is on-demand VMs. Note that sustained VMs, sustained use, and customized VMs also come under this category, where computing normalized cost is very straightforward. That is, we simply assign the on-demand cost to each unit of resource demand. Transient VMs are complex to model when it comes to normalized cost, as we need to consider job length, which prevents us from directly computing it under the assumption of fractional resource demand. For example, for the transient VM option, the longer the job runs, the higher the risk that the transient VM will get revoked, hence higher its normalized cost. Also, we ensure that a job assigned to transient VM completes. In case the transient VM doesn't get revoked, it's fine. But in case it gets revoked, we make sure that the job gets run on on-demand VM, so that it finishes and reduces the risk of getting revoked again. Hence, in order to compute normalization cost, we need to consider both the scenarios where the transient VM is available throughout the job duration, and in other cases, we need to consider case where transient VM gets revoked. That is reflected in this formula, where the first term reflects that transient VM is available throughout the duration of the job, whereas in the second term, it reflects that transient VM gets revoked and it again gets rescheduled on an on-demand VM, and our expected cost is a weighted average of these two terms. Next, moving on to spot blocks. These are a special case of spot VMs, and as we have discussed before, these are built R, and given higher duration, you get lower discount compared to lower durations. And in the offline case, since we have the precise knowledge of how much time a job runs, we can definitely know if a job can be runnable or spot block or not. In case it is runnable on spot block, and here we don't assume any revocation, and so we simply assign spot block cost to job cost, similar to on-demand case. But in the case of online case, we can't assume or else predict the job runtime precisely. Hence, we treat spot blocks as transient VMs. Also note that spot blocks are slightly more expensive than transient VMs as well. Next, coming to reserve VMs. Reserve VMs are very similar, are easier to compute as well, as all we need to do is we need to take a look at resource demand, and we need to know its utilization across all time units, time commitment. Then what we need to do is we divide this utilization we divide the cost by the utilization, and that gives us normalized cost. And also note that in offline case, we assume reserve VMs as fractional resources. That makes the job easier. In this illustrated example, we assume 1 year reserved option. Hence, we get 40% discount. So its price is 60% of on-demand cost. So if the utilization is around 60%, that means that normalized cost is same as on-demand cost. And if the utilization is higher, the normalized cost of on-demand is higher than reserved, hence making reserved a best option, and vice versa. Hence, this diagram reflects the same thing, where the on-demand is selected when utilization is lower than 60, and if utilization is higher than 60, reserve becomes a better option. Similarly, scheduled reserves, the computation is similar, but we must consider several different schedules available, as there are a lot of daily, weekly, monthly schedules possibly available. And our task here is to select multiple such schedules such that we maximize the discount or minimize the cost. Here, we reduce this problem of finding schedules to a dynamic programming problem, where we select multiple jobs in a weighted job scheduling, where the task is given a fixed compute hardware resources. We need to select multiple jobs to run on that hardware to maximize value, where each job is associated with a value. Hence, in our approach, each possible schedule is akin to a job in weighted job scheduling, and normalized discount associated with this scheduled reserve is akin to its value, and our task is to select multiple such schedules. Hence, the output is a cheapest set of schedules in this problem. Now that we have talked about how we compute different normalization options, let's talk about how we consider these purchasing options in an order. The order matters because, for example, if you pick a reserve VM, what happens is that reserve VM, we have to use it for an entire year. Hence, we cannot use any other option for that entire year for that resource demand. So first what we do is we start with a no commitment or else lowest time commitment and move to a higher time commitment when it comes to picking a resource demand here. So after we have after we transform our workload as a time varying function of resource demand, next what we do is for each resource demand, we try to pick cheapest option first from transient VM, spot block, on demand and reserved, scheduled reserved. And next we compare the cheapest of these to 1 year reserved. And next we consider 3-year reserve. In this way, we always pick the cheapest possible option available for each unit. And note that once we pick reserved option, we need not consider doing this process for the next time unit in that next unit time. Next, let's talk about our practical approach, as our offline approach is highly ideal and it's not realistic in real world. Our practical approach is similar in terms of offline policy, but there are two key differences where we utilize predictions in the place of assuming perfect knowledge, and we don't assume a fractional supply and demand where we map the jobs to a specific type of VMs, taking their requirements into account. And note that our online approach is a heuristic, as we have imperfect knowledge of workload, as well as we relax the assumption of fractional supply and demand where bin packing becomes harder in case of reserve VMs. Hence, our approach is biased towards larger VMs in the case of reserve VMs, as they allow us to run higher number of jobs and larger jobs, and packing can be a bit simpler than smaller jobs. Coming to how our algorithm approaches, given a huge amount of data, our online approach, what it does is it takes initial data as training and uses offline algorithm to estimate how much reserve capacity to buy, and we assume here that or whatever the training period can predict the future or else testing with a precise or else in good accuracy. So once we purchase reserve capacity based on our offline approach and training data, later as the jobs arrive in testing data, we schedule them on available reserve VMs based on their reserve requirement. If we cannot, what we do is we dynamically try to acquire non-reserve options like transient, reserved, a transient scheduled reserved, and on-demand VMs based on their normalized cost. So we keep repeating this process until all the jobs in testing is done. Coming to implementation, we have implemented our policies using Python and NumPy and Pandas libraries. For evaluation and validation, we use a workload trace from an academic batch cluster that consists of 14,376 cores, and this dataset consists of 60 million batch jobs for about 4-year duration, where each job entry includes a submission time, number of requested cores, how much memory required, and how much time that job has run. In evaluation, we evaluate the cost benefits of using a mix of VM purchasing options by comparing them to solely using one option like reserved or on demand. Also, we compare online policy to offline policy to give an idea about how far our online policy is behind our offline policy in terms of cost benefits. And also, we compare cost benefits among different cloud providers, as each cloud provider offers some unique offering and we want to measure how much benefit they bring to the table. Also, in the case of online approach, we use first year, that is 2015 years data as training, and we use next 3 years, that is 2016 to 2018 for testing or evaluation purpose. First, let's look at our batch trace characteristics before we get into our graphs or results. Here we plot time varying function of core demand for 2015 year. As you can see here, the requirement varies rapidly, and there are load bursts pretty often. And there are times where the core requirement is higher than 14,000 and it can reach maximum of 40,000. It's very high. Hence, our trace is very bursty. Now let's look at how the job length varies in this trace. Here we use three different buckets. First is 0 to 6 hours, another is 6 to 24 hours, and finally another bucket is greater than 1 day, which is longer jobs. Here we pick specifically 6 because spot blocks have maximum duration of 6. Hence, in that concept, we picked 6 hours here. On the x-axis, you have year. On the y-axis, you have proportion of jobs. As you can see here, there is predominantly high number of smaller jobs compared to longer jobs, and it can be seen the same trend across multiple years as well. Hence, the trace consists of significant amount of shorter jobs, less than 6 hours. In our results, first let's look at how our optimistic offline policy performs against solely using on-demand for workloads. Here we use 3 years data. One is 2016, 2017, 2018, and we repeat this experiment for using Microsoft model, Amazon model, Google standard, Google customized. Note that Microsoft is strictly a subset of Amazon, where Amazon offers on top of common purchasing options, spot block and schedule reserved. As you can see here, our offline policy offers significant discount compared to using only on demand, where the discount can range from anywhere between 60 to 50%. And in all of the cases, Google customized seems to give highest discount thanks to its customized options, where the on-demand VMs that users jobs can fit on perfectly without wasting the compute resources there. On the other hand, we see that Microsoft and Amazon are very close. It's because even though Amazon offers more options, but its schedule reserved offers significantly lesser discount, like 5 to 7%, and finding right set of schedules is complex here. As a result, Microsoft and Amazon looks very similar. Let's look at a breakdown among these options on how transient, reserved, on-demand VMs, the cost varies. As you can see here, on the x-axis, you have different cloud providers. On the y-axis, you have cost proportion. And here we plot transient, reserved, on-demand. As we have discussed before, scheduled reserved offers very poor amount of discount, and it's harder to find right set of schedules. And in on-demand, we have both sustained discount in the case of Google as well. As you can see here, across all of these cloud platforms, on-demand cost dominates other two options. It's because of the load burst, and when it comes to load burst, we have no option other than to go for on-demand, as picking the reserved for peak results in very, very high cost. And coming to Google, the on-demand is higher than both Microsoft and Amazon. It's because of sustained use discount, and sustained use discount give as high as 30% discount, and it is comparable to 40% discount that you get in 1 year reserved as well. Next, let's compare our practical online approach and how it performs against offline policy. In this case, we use previous year to estimate the percentage, estimate the number of reserved records. For example, for 2016 year, we use 2015 data and offline policy to estimate the number of reserve. And similarly, for 2017 here, we use 2016 data and offline approach to estimate reserved, and so on. And we plotted the data here. As you can see here, in all of the years, our practical online offline policy performs better than online policy. It's because of its assumptions, and in the case of online approach, we have imperfect predictions as well as relaxed assumption of fractional supply and demand. As a result, online approach performs worse than offline, and it can be seen that it is within 35 to 55% greater cost than offline policy, which is strictly the lower bound on the cost. Hence, in conclusion, we presented multiple policies to optimize long-term costs by selecting a mix of VM purchasing options. Here, we account for uncertainty in future workloads, and we propose both offline optimal, which is an opt, and a practical online policy. We have evaluated our policies on a batch trace spanning 4 years, and our online policy incurs a cost within 41% of an optimal offline policy, and our online policy costs strictly 50% less than solely using on-demand VMs, and 79% less than uh, using reserve VMs only.